We can use this patch. Uh, we can use this to patch the lack of an implement's keywords by explicitly having a function inherit an interface. Next, coffee flavor implements coffee order interface and must contain its interface methods for us to assign the functionality powering these implementations to an object. So here we have coffee interface, then implement interface for coffee order, then sample usage, then place orders, serve orders, converting code to use the flyweight pattern. Next, let's continue our look at flyweights by implementing a system to manage all books in a library. You could list the essential metadata for each book as follows: ID, title, author, genre, page count, publisher ID, ISBN. We'll also require the following properties to track which member has checked out a particular book, the date they've checked it out, and the expected return date. Checkout date, it could be this checkout date name, or this could be like the properties: checkout date, checkout member, due return date, availability. So this is all in one word. The checkout date is in one word, checkout member one word, due return date one word, then availability. Then we create a book class to represent each book as follows before any optimization using the flyweight pattern. The constructor takes in all the properties related directly to the book and those required for tracking it. This probably works fine initially for small collections of books. However, as the library expands to include a more extensive inventory with multiple versions and copies of each book, we may find the management system running more slowly. Using thousands of book objects may overwhelm the available memory, but we can optimize our system using the flyweight pattern to improve this. We can now separate our data into intrinsic and extrinsic states. Data relevant to the book object, title, author, etc. is intrinsic, while the checkout data, checkout member, due return date, etc. is considered extrinsic. Effectively, this means that only one book object is required for each combination of book properties. It's still a considerable number of objects, but significantly fewer than we had previously. An instance of the following book metadata combination will be created for all required copies of the book object with a particular title or ISBN. As we can see, the extrinsic states have been removed. Everything to do with library checkouts will be moved to a manager. And as the object data is now segmented, we can use a factory for instantiation. A basic factory. Let's now define a very basic factory. We will have it check if a book with a particular title has been previously created inside the system. If it has, we'll return it. If not, a new book will be created and stored so that it can be accessed later. This ensures that we create only a single copy of each unique intrinsic piece of data. Here's the book factory singleton, const existing books equal open and close, semicolon, semicolon. Managing the extrinsic states. Next, we need to store the states that were removed from the book object somewhere. Luckily, a manager which will be defining as a singleton can be used to encapsulate them. Combinations of a book object and the library member who's checked it out will be called book record. Our manager will be storing both and will include checkout related logic we strip out during our flyweight optimization of the book class. The result of these changes is that all of the data extracted from the book class is now being stored in an attribute of the book manager singleton the book database, something considerably more efficient than the large number of objects we were previously using. Methods related to book checkouts are also now based here as they deal with extrinsic rather than intrinsic data. This process does add a little complexity to our final solution. However, it's a minor concern compared to the performance issues that we have tackled. Data-wise, if we have 30 copies of the same book, we're now storing it only once. Also, every function takes up memory. With the flyweight pattern, these functions exist in one place, on the manager, and not on every object, thus saving on memory use. For an optimized version of flyweight mentioned previously, we store just a link to the function object as we use the book constructor's prototype. Still, if we implemented it another way, functions will be created for every book instance. The flyweight pattern and the DOM. The DOM supports two approaches that allow objects to detect events, either top-down event capture or bottom-up event bubbling. In event capture, the event is first captured by the outermost element and propagated to the innermost element. In event bubbling, the event is captured and given to the innermost element and then propagated to the outer elements. Gary Chisholm wrote one of the best metaphors for describing flyweights in this context, and it goes a little like this. Try to think of the flyweight in terms of a pond. A fish opens its mouth, the event. Bubbles rise to the surface, the bubbling. A fly sitting on top flies away when the bubble reaches the surface, the action. In this example, we can easily transpose the fish opening its mouth to a button being clicked, the bubbles as the bubbling effect, and the fly flying away to some function being run. Bubbling was introduced to handle a situation in which a single event, like a click, may be handled by multiple event handlers defined at different levels of the DOM hierarchy. Where this happens, event bubbling executes event handlers defined for specific elements at the lowest level possible. From there on, the event bubbles up to containing elements before going to those even higher up. Flyweights can be used to further tweak the event bubbling process, as we will see in example centralized event handling. Example, centralized event handling. For our first practical example, imagine we have several similar elements in a document with similar behavior executed when a user action, i.e. click, mouse over is performed against them. Usually, when constructing our accordion component, menu or other list-based widgets, we bind the click event to each link element in the parent container, i.e. ul lia.on. Instead of binding the click to multiple elements, we can easily attach a flyweight to the top of our container, which can listen for events coming from below. These can be handled using logic as simple or complex as required, as the types of components mentioned often have the same repeating markup for each section, i.e. each section of an accordion. There's a good chance the behavior of each element clicked will be pretty similar and relative to similar classes nearby. We'll use this information to construct a basic accordion using the flyweight in example 7.6. A state manager namespace is used here to encapsulate our flyweight logic, while jQuery is used to bind the initial click to a container div. An unbind event is first applied to ensure that no other logic on the page attaches similar handles to the container. To establish exactly what child elements in the container is clicked, we use a target check which provides a reference to the element that was clicked, regardless of its parent. We then use this information to handle the click event without actually needing to bind the event to specific children when our page loads. Centralized event handling. example 7.6. The benefit here is that we're converting many independent actions into shared ones, potentially saving on memory. Behavioral patterns. Behavioral patterns help define the communication between objects. They help to improve or streamline the communication between disparate objects in a system. Following are the JavaScript behavioral patterns that we will discuss in this section. The observer pattern, the mediator pattern, the command pattern. The observer pattern. The observer pattern allows you to notify one object when another object changes without requiring the object to know about its dependence. Often this is a pattern where an object, known as a subject, maintains a list of objects depending on it, observers, automatically notifying them of any changes to its state. In modern frameworks, the observer pattern is used to inform components of state changes. Figure 7.9 illustrates this. Observer pattern, subject, add observer, remove observer, then notify. Then an observer update. Then another is concrete observer. Then we have state of subject, then update. Then for another we have concrete subject, state of subject, get state. Then return state of subject for that concrete subject, and for concrete observer earlier, state of observer equals subject that gets state function. When a subject needs to notify observers about something interesting happening, it broadcasts a notification to the observer which can include specific data related to the topic. When an observer no longer wishes to be notified of changes by the subject, they can be removed from the list of observers. It's helpful to refer back to published definitions of design patterns that are language agnostic to get a broader sense of their usage and advantages over time. The definition of the observer pattern provided in the GOF book, Design Patterns, Element of Reusable Object-Oriented Software, is one or more observers are interested in the state of a subject and register their interest with the subject by attaching themselves. When something changes in our subject that the observer may be interested in, a notify message is sent which calls the update method in each observer. When the observer is no longer interested in the subject state, they can simply detach themselves. We can now expand on what we've learned to implement the observer pattern with the following components. Subject maintains a list of observers, facilitates adding or removing observers. Observer provides an update interface for objects that need to be notified of a subject changes in state. Concrete subject broadcasts notifications to observers on changes of state, stores the state of concrete observers. Concrete observers stores a reference to the concrete subject, implements an update interface for the observer to ensure the state is consistent with subjects. ES 2015 Plus allows us to implement the observer pattern using JavaScript classes for observers and subject with methods for notify and update. First, let's model the list of dependent observers a subject may have using the observer list class. Next, let's model the subject class that can add, remove, or notify observers on the observer list. We have class object, add observer method, and then remove observer method and notify method in this. We then define a skeleton for creating a new observers. We will override the update functionality here later with custom behavior. So we have class observer. In our sample application, using the previous observer components, we now define a button for adding new observable checkboxes to the page. A control checkbox will act as a subject, notifying other checkboxes that they should update to the check state. Then a container for the new checkbox added.